In this review video, we'll work through a set of real exam-style Calculus 1 problems on derivative basics. These are the same types of problems I used to give my university students to review for their exams, and the examples come directly from my Calculus 1 course videos, just the problem-solving portion without the lecture, so you can stay focused on the examples. You can also download the free PDF of all the practice problems on my website, understandthemath.com. Let's get started. In our first example, using the definition of the derivative, we are going to find the derivative of the function f of x is equal to 3x squared minus 4x plus 1 at the number a. There are two limit definitions of the derivative that we can choose, and I'm going to choose the one that has the h in the denominator. This is f prime at a is equal to the limit as h goes to 0 of f of a plus h minus f of a, all divided by h. Now we're going to substitute in. Wherever we have an x, we're going to plug in a plus h. This is 3a plus h squared minus 4a plus h plus 1 minus our function f of a, and wherever we have an x, we're going to plug in a. So this is 3a squared minus 4a plus 1. And we divide all of this by h. Now we have to do some algebra and multiply some things out. This gives us the limit as h goes to 0. I'm going to multiply this out first. So we have 3. This is a squared plus 2ah plus h squared. Now let's do some simplification. This is minus 4a minus 4h plus 1. And then we have minus 3a squared plus 4a minus 1. And all of this gets divided by h. I want to show you before we go on the most common mistake I see students make when they do a calculation like this. It's this part right here. You have to remember that this negative gets distributed to all three of those terms. Now all we have to do is multiply things out. This is the limit as h goes to 0, 3a squared plus 6ah plus 3h squared. And now before we go ahead and copy down all those terms again, let's see if anything cancels. Do you see that the minus 4a cancels with the 4a and the 1 cancels with the 1? Now we don't have to write those down again. And all we have to write down is minus 4h minus 3a squared. And then we have our h in our denominator. Let's again look and see what cancels. This term cancels with this term, and nothing else cancels, but notice these three terms. Do you see that they all have an h common to them? Because of that, we can go ahead and we can pull an h out. So this is the limit as h goes to 0 of h. We have a 6a plus 3h minus 4, all divided by h. Now our h's cancel, and we can go ahead and just substitute in that h is equal to 0, and this gives us an answer of 6a minus 4. And that is the derivative of our function at the number a. Let's now look at another example. Whenever I used to give this example on a quiz or a test, it was usually the most missed problem. I want to make sure that you understand how to do this. The following limit represents the derivative of some function f at some number a. We are asked to find f and find a. The way you want to begin a problem like this is to write down the definition of the derivative that corresponds to the limit that you're given. In part A, our limit is going to correspond to this definition of the derivative. F prime at A is the limit as h goes to 0 of f of a plus h minus f at a, all divided by h. Now what we're going to do is we are going to compare our formula to the limit that we are given. Our f of a plus h is equal to the square root of 9 plus h. Let's write that down. F of a plus h is the square root of 9 plus h, and then f of a is equal to 3. With this information, we can find out what f and a are equal to. A plus h is equal to 9 plus h. So this tells us that a is equal to 9, and then f at a plus h is equal to the square root of a plus h. We want to know what f of x is. To find f of x, wherever we see an a plus h, we're going to substitute in x. So f of x is just the square root of x. Now, this problem has a really nice built-in check, and that built-in check uses the other piece of information that we haven't used yet. F of a is equal to 3. So let's just go down here to our function and say that f of a is equal to f at 9, which is the square root of 9, which is 3, and that agrees. So we know we've done the problem right. Let's look at part B. This limit is similar to this definition of the derivative. F prime at a is the limit as x goes to a of f of x minus f of a, all divided by x minus a. Now let's go ahead and let's equate things. F of x is going to be x to the 6th. So we write down f of x is x to the 6th, and then f of a is 64. To find a, all we need to do is compare our limits. X goes to a is the same as x goes to 2, so that tells us that a is equal to 2. So we found that f of x was x to the 6th and a was equal to 2. And here's our built-in check. We're told that f of a is equal to 64. Let's see if that's true. F of a is f at 2, which is 2 to the 6th, which is indeed 64. So we know we've done the problem right. Let's now walk through some examples where we're going to find the derivative of the given function using the definition of the derivative. We're also going to state the domain of the function and then the domain of its derivative. I'm going to begin by writing down the formula for the derivative. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Now we're going to substitute in what f of x plus h is and what f of x is. Wherever we see an x, we're going to substitute in x plus h. So this is 5 times x plus h minus 4. And now we're going to subtract off f of x, which is 5x minus 4. And all of this is divided by h. Now all we have to do is just do a little bit of algebra. This is 5x plus 5h minus 4 minus 5x plus 4. Make sure that you carry this negative through to both this term and this term. And then all of this gets divided by h. Now let's see if we have anything that cancels. Our 5x cancels, and then our minus 4 cancels with 4. So this gives us the limit as h goes to 0 of 5h divided by h. And now you can see that the h's cancel, and we're left with a value of 5. So the derivative of our function is equal to 5. Now we're going to find the domain of f of x and the domain of f prime of x. I'm going to write this up here at the top. The domain of f of x is going to be minus infinity to infinity because our function f of x over here on the left is just 5x minus 4. That is a polynomial, and a polynomial is continuous everywhere. Now let's talk about the domain of our derivative. Our derivative is equal to a constant 5, and that is continuous everywhere. So the domain of our derivative is also minus infinity to infinity. Let's now look at our second example. This is just a classic example to do when you're first learning about derivatives. We want to find f prime of x, so let's start with our formula. I think you'll find if you write the formula down each time you do a problem, you will begin to memorize it. We have f of x plus h minus f of x, all divided by h. This is the limit as h goes to 0. Wherever we have an x, we're going to substitute in x plus h, and this gives us the square root x plus h minus f of x, which is the square root of x, all divided by h. When we plug in that h goes to 0, we are going to get square root of x minus square root of x, which is 0 over 0. That is an indeterminate form. I have a video on evaluating limits with indeterminate forms like this if you need to review that. To evaluate this limit, notice that we have a square root minus another square root. That tells us that we should multiply by the conjugate. Let me write up here what the conjugate is. The conjugate of the square root of a minus the square root of b is the square root of a plus the square root of b. I'm going to go ahead and I'm going to erase the 0 over 0 just because we're going to run out of space if I don't. And now we're going to multiply by the conjugate. The conjugate is the square root of x plus h plus the square root of x. And we're also going to divide by that. And the reason that we have to do that is we can't change the limit. So we can only multiply by 1, which is what we just did. Now let's go ahead and let's use the FOIL method to solve this. I'm going to put parentheses around this top piece so it makes it easier. The FOIL method says the first thing we do is multiply the first terms, and that is the square root of x plus h times the square root of x plus h, so that just gives us x plus h. And now we're going to multiply the outer terms. So this is the square root of x plus h times square root of x. Now we multiply the inner terms, which is minus root x plus h. And then we multiply the last terms, which gives us a minus x, because that's square root of x times square root of x. And all of this is divided by h times the square root of x plus h plus root x. Now let's go ahead and let's see what cancels. we have an x that cancels, and then these terms with the square roots cancel, which is really nice. So let's see what we have left. This is the limit. As h goes to 0, we have an h on top, and then we have an h times the square root of x plus h plus root x. Now you can see that our h's cancel. And then we can go ahead and we can substitute that h is equal to 0. So this gives us an answer of 1 divided by 2 square root of x. And that's our answer. So the derivative of root x is 1 divided by 2 root x. We have one last thing to do, and that is to look at the domains. I'm going to do that over here on the left. So we can write down the domain of f of x. Now, whenever we have a square root, whatever is inside the square root has to be greater than or equal to 0. So our domain is going to be from 0 to infinity. Now let's look at the domain of our derivative. Our derivative is 1 divided by 2 times the square root of x. And because the square root of x is in the denominator, we know that x cannot be 0. So our domain is going to be an open bracket at 0 to infinity. Let's now look at an example where we are given the graph of a function f, and we want to state where the function f is not differentiable. Over here on the right, just as a reminder, I wrote down that a function will not be differentiable if it has a removable jump or infinite discontinuity, or if the function has a corner, a vertical tangent, or a cusp. Let's start looking at our x values as we go from left to right. When x is equal to -5, we have what looks like a cusp. So at x is -5, our function is not differentiable, and the reason is that we have a cusp. Let's now look at x is equal to -4. At that point, we have an infinite discontinuity, so our function is not continuous, and that means that our function is not differentiable. So let's write down x is equal to -4. We have an infinite discontinuity. Now let's look at the next point. That point is going to be -2, and at that point, we have a removable discontinuity. So our function is not continuous, and that means that our derivative is not continuous. So we'll write down x is equal to -2. We have a removable discontinuity. Now let's go over to where x is equal to 1. Here we have what's called a jump discontinuity. So our function is also not differentiable at x is equal to 1. And we'll write down jump discontinuity. And then we have one more point to look at, and that is where x is equal to 3. And notice on our graph that we have a vertical tangent at that point. So at x is equal to 3, our function is continuous, but the derivative is not differentiable. So we can say that we have a vertical tangent there. And that is why our function is not differentiable. Let's look at some examples where we are going to use the power, sum, and difference rules to differentiate each function. Let's look at our first example. Our function is 2x cubed minus 3x squared minus 4x. Our derivative can be written as f prime of x is equal to the derivative with respect to x of 2x cubed minus 3x squared minus 4x. We are going to take the derivative of each piece, and whenever we have a constant, we can just pull that constant out in front of the derivative. So our first piece looks like this. It's 2 times the derivative with respect to x of x cubed minus 3 times the derivative with respect to x of x squared minus 4 times the derivative with respect to x of x. Now we're going to take our derivatives. Our first piece has 2, and then the derivative of x cubed is 3x squared. You just subtract 1 from the exponent, minus 3 times the derivative of x squared, which is 2x, minus 4 times the derivative of x, which is just 1. We can now write our answer as 6x squared minus 6x minus 4. When you get used to doing this, you can probably just write that answer down without going through any of these in-between steps. Let's now look at our second example. We are going to take the derivative of y is equal to x squared plus 4x plus 3, all divided by the square root of x. To use the power rule, we need each term in this function to be raised to a power, and we can't have a denominator. So let's start by rewriting this function and get rid of the denominator. This gives us y is equal to x squared divided by x to the 1/2 plus 4x divided by x to the 1/2 plus 3 all divided by x to the 1/2. We can split this up because we only have one term in the denominator. Let's now rewrite this. This is y is equal to x to the 3/2. I got that because we can think of 2 as 4 divided by 2, and then we just took 4 and subtracted 1. And then for our next term, we have 4x to the 1/2. This is just 1, and then we subtracted a half. And then our last term is 3x to the minus 1/2. Just bringing that 1/2 up on top. Now we can go ahead and take our derivative. Our derivative is dy dx, and it is the derivative with respect to x of our first piece, x to the 3/2, plus our derivative with respect to x of our second piece, 4x to the 1/2. And then lastly, in our third piece, there is a 3 sitting there. We can pull that out in front and then multiply that by the derivative with respect to x of x to the minus 1/2. We could have also pulled out the 4 in the second term. Now we can take the derivative of all 3 pieces. Our first derivative is 3/2 x to the 3/2 minus 1. And then our next piece, we pull out the 4, and then we take the derivative, which is 1/2 x to the 1/2 minus 1. And then our last piece, we're going to take our 3, multiply it by minus 1/2. So we get minus 3/2 times x to the minus 1/2 minus 1. This then gives us 3/2 x to the 1/2 power plus 2x to the minus 1/2 power minus 3/2 x to the minus 3/2 power. Now, it looks like we could be done, but notice, let me pull this back down. Notice in our original problem, we had a square root of x. So that kind of clues us in that our answer needs to be in terms of square roots and not just in terms of x to the 1/2. So I'm going to rewrite this as 3/2 times the square root of x plus 2 all divided by square root of x minus 3 all divided by 2, and then x to the minus 3/2 becomes x to the 3/2 when we put it in the denominator, and then x to the 3/2 can be written as x times square root of x. Let me just make a note over here so this is clear. This is 1 over x to the 3/2, which we then wrote as x times the square root of x. And there is our final answer. In this example, we are going to find equations of the tangent line and the normal line to the curve y is equal to 2x cubed minus x squared plus 2 at the point 1, 3. I'm going to start by finding the equation of the tangent line, and let's go ahead and let's write down what that equation looks like. That equation looks like y minus y1 is equal to the slope times x minus x1. The first thing that we need to do is find the slope. So the slope of our equation is the slope of the tangent line to the curve, and that is given by dy dx. And we want to find that at the point 1, 3. So that means x is equal to 1. So I'm just going to put down x is equal to 1. So what we're doing is we're finding the derivative at the point x is equal to 1. Let's write down what our derivative is. That is going to be the derivative with respect to x of 2x cubed minus x squared plus 2 evaluated at the point x is equal to 1. This is equal to 6x squared minus 2x, and then the derivative of 2 is 0. And we are going to evaluate this at x is equal to 1. So this becomes 6 minus 2, which is 4. So our slope is equal to 4, and we can plug that into our equation. We are given that x1 and y1 is the point 1, 3. So we can write this as y minus 3 is equal to our slope, which is 4, times x minus 1. Now, it's always nice to write this in slope-intercept form. So I'm going to bring the 3 to the right and multiply things out. This gives us y is equal to 4x minus 4 plus 3. And this gives us an answer of y is equal to 4x minus 1. And that is the equation of the tangent line to our curve at the point 1, 3. Now let's look at the second piece of this problem. We want to find the normal line. The normal line is perpendicular to the tangent line. So the slope of the normal line is going to be the negative reciprocal of the slope of the tangent line, which is minus 1 over m. So it's going to be minus 1 over m, which was 4. Now we do the same thing. Let's write down our general equation. Y minus y1 is equal to our slope. We'll go ahead and put in minus 1/4 x minus x1. Now we're going to substitute in that y1 is 3, x1 is 1. So this gives us y minus 3 is minus 1/4 x minus 1. Now let's multiply everything through. This is y is equal to minus 1/4 x plus 1/4 plus 3. Let's think of our 3 as 12 over 4. So our final answer is y is minus 1/4 x plus 12 over 4 plus 1 over 4 is 13 over 4. And let's highlight this because that is the equation of our normal line. In this example, we're asked for what value of x does y equal 2e to the x minus 2x have a horizontal tangent. I think the hardest part of this problem is trying to figure out what you actually need to calculate. So let's look at this again. For what value of x? So we need to find x where our function has a horizontal tangent. A horizontal tangent is going to happen where the slope of our curve is equal to 0. So that means we want to find x where our slope or our derivative dy dx is equal to 0. This means that the way we're going to start is by finding the derivative and setting it equal to 0, and then we're going to solve for x. Let's go ahead and let's take our derivative. Dy dx is the derivative with respect to x of 2e to the x minus 2x. This is 2 times the derivative of e to the x, which is just e to the x, minus the derivative of 2x, which is minus 2. And we need to set that equal to 0. Let's go ahead and let's pull the 2 over to the right-hand side. So this is 2e to the x is equal to 2. Dividing each side by 2, we get that e to the x is equal to 1. You may know by looking at a graph of e to the x that e to the x is going to be equal to 1 when x is equal to 0. If you don't know that, one way that you can solve this is by taking the natural log of both sides, because that will get the x out of the exponent. This then is x times natural log of e is equal to the natural log of 1. Then we have to know that the natural log of e is 1. So on the left-hand side, we just have x. And then we have to know that the natural log of 1 is equal to 0. So we get x is equal to 0. I have a video on the natural exponential and natural logarithmic function that you may want to look at if you're rusty on exponentials and logs. Let's go ahead and let's highlight our answer. This tells us that our curve has a horizontal tangent at x is equal to 0. I went ahead and graphed this curve just so that you can see this. Do you see that right here at this point, x is equal to 0, we have a horizontal tangent. In this example, we are going to use the product rule to calculate the derivative. In part A, we're going to be finding the derivative of the function f of x is equal to x cubed times 2x squared plus 1. X cubed is our first function, and then 2x squared plus 1 is our second function. Let's now calculate the derivative. The derivative can be written as f prime of x, and it is the first function, x cubed, times the derivative of the second function, which is 2x squared plus 1, plus the second function, 2x squared plus 1, times the derivative of the first function, which is x cubed. Now all we have to do is just calculate these derivatives. We have x cubed, and then the derivative of 2x squared plus 1 is 4x. And then we have 2x squared plus 1 times the derivative of x cubed, which is just 3x squared. Now what we need to do is multiply everything out. This first product is 4x to the fourth. And then our next term gives us a 2 times 3, which is 6. And then x squared times x squared is x to the fourth. And then we just have a 3x squared left. We can combine our x to the fourth terms, and we end up with 10x to the fourth plus 3x squared. And that's our derivative. Let's now look at part B. In part B, we are going to be differentiating the function f of x is equal to 3x minus 5, that is our first function, times 4x squared minus 3, and that's our second function. Our derivative then is f prime of x, and it is the first function, 3x minus 5, times the derivative of the second function, which is 4x squared minus 3, plus the second function, 4x squared minus 3 times the derivative of the first function, which is 3x minus 5. After you get used to doing this, you can probably not write down this step and just do the derivative in your head. We now have 3x minus 5, and then the derivative of 4x squared is going to be 8x, and the derivative of minus 3 is 0. And then we have 4x squared minus 3 times the derivative of 3x minus 5, which is just 3. Let's now multiply everything out. 3x times 8x gives us a 24x squared. And then minus 5 times 8 is minus 40. And there's an x that goes with that. And then if we look at our second piece, we have 4 times 3. So that's 12x squared. Minus 3 times 3 gives us a minus 9. Now let's see what we can combine. It looks like we can combine this term and this term. 12 and 24 is going to be 36. So we have 36x squared minus 40x minus 9. And that's our derivative. It's really nice when you're working with polynomials. When you get to your final answer, make sure to write your answer with the largest exponent first, and then the constant term should be last. Let's now look at our second example. In this example, we are given h of x is equal to x times g of x. We're given that g of 3 is equal to 5, and that the derivative of g at the point 3 is equal to 2. We are then asked to find h prime of 3. Let's start by writing down our function. We are given that h of x is equal to x times g of x. We want to find the derivative, so let's write down h prime of x. Notice that h is the product of two functions. X is our first function, and g of x is our second function. So we'll use the product rule. We have the first, which is x, times the derivative of the second, which is g prime of x, plus the second, which is g of x, times the derivative of the first. The derivative of x is just 1, so we'll multiply g of x times 1. Now what we're going to do is plug in that x is going to equal 3. So we have h prime at 3 is equal to 3, g prime at 3, plus g of 3. Now we can go ahead and substitute in what g prime of 3 is and what g of 3 is. This gives us 3 times g prime of 3, which is 2, plus g of 3, which is 5. So let's see, this is 6 plus 5, so we get an answer of 11. In this example, we are going to use the quotient rule to calculate the derivative. In part A, our function f of x is x squared plus 1. That is the top function. And it's divided by x cubed minus 1, which is the bottom function. Our derivative, f prime of x, is the bottom function, x cubed minus 1, times the derivative of the top function, x squared plus 1. So that's just low d high. And then we have to subtract the top function, x squared plus 1, times the derivative of the bottom function, x cubed minus 1. That's just high d low. And then we're going to divide all of this by the bottom function squared, or you can think of that as the square of what's below. Now we just have to do some derivatives. We have x cubed minus 1, and the derivative with respect to x of x squared plus 1 is just going to be 2x. And then we subtract x squared plus 1. And then the derivative of x cubed minus 1 is just 3x squared. And again, we have all of this divided by x cubed minus 1 quantity squared. Now let's look at our numerator and let's multiply everything out because some terms are going to combine. X cubed times 2x gives us 2x to the fourth, and then we have a minus 2x. Then we have x squared times 3x squared. That gives us a minus 3x to the fourth. And then the last term is going to be 1 times 3x squared, and that gives us a minus 3x squared. Make sure that you remember that this minus term is going to carry over to both terms. And then all of this is divided by x cubed minus 1 squared. Now let's see what terms combine. We can combine 2x to the fourth with minus 3x to the fourth, and that gives us a minus x to the fourth, and then we have a minus 3x squared, and then minus 2x, and all of that is divided by x cubed minus 1 quantity squared. Notice that in the numerator, I wrote the terms in descending order. You just put the highest power first, and then the next highest power until you have all the terms written. It just makes your answer look a lot nicer if you do that. And here is our final answer. Let's now look at part B. In this example, we are taking the derivative of f of x is equal to the square root of x, that's our top function, divided by 2 plus x, that's our bottom function. We're going to use the quotient rule, and it tells us that f prime of x is the bottom term, 2 plus x, times the derivative with respect to x of our top term. And I'm going to write the square root of x as x to the 1/2 because it's going to make it easier to take the derivative if we write it that way. And then we subtract off the top term, x to the 1/2, times the derivative of the bottom term, which is 2 plus x, all divided by the bottom term squared. Now let's go ahead and let's take some derivatives. We have 2 plus x. The derivative of x to the 1/2 is 1/2 x to the minus 1/2. And then we subtract off x to the 1/2. And the derivative of 2 plus x is actually just 1. And then all of this is still divided by 2 plus x quantity squared. Now let's go ahead and let's look at this top piece right here, and let's multiply that out. We have 2 times 1/2 is 1, so our first term is just x to the minus 1/2, and then we have a plus 1/2, x times x to the minus 1/2. Remember that x just has a power of 1, so it's 1 minus 1/2, which gives us an x to the 1/2, and then minus x to the 1/2, all divided by 2 plus x quantity squared. Now let's see what we have. It looks like we can combine this term and this term. So we have x to the minus 1/2 minus 1/2 x to the 1/2, all divided by 2 plus x quantity squared. When you use the quotient rule, most of your time is going to be spent on algebra simplification. I think it's going to be easiest to simplify our numerator if we rewrite it in terms of square root of x. Let's write this as 1 divided by root x minus root x, all divided by 2, all divided by 2 plus x quantity squared. I think the easiest way to simplify this is if we multiply the top and the bottom by 2 root x. That is just going to clear out our fractions that we have in our numerator. Our first term is going to be 2 root x divided by root x, and that is going to be 2. And then we have 2 root x times root x divided by 2. The square roots are going to combine, and we're going to get an x, so we have a minus x. And then the 2's cancel, which is really nice. And in our denominator, I'm going to pull the 2 root x out in front, and then multiply this by 2 plus x quantity squared. And there is our derivative. In this example, we are given that h of x is g of x divided by x, g of 2 is equal to 4, and then g prime of 2 is negative 4, and we're asked to find h prime at 2. We are given that h of x is g of x all divided by x. G of x is our top function, and then x is our bottom function. H prime of x is going to be x, the bottom function, times the derivative of the top, minus the top, which is g of x, times the derivative of the bottom, which is the derivative of x, which is just 1. And we're going to divide all of that by our bottom function squared. Now what we're going to do is we're going to substitute in that x is equal to 2. So we have h prime at 2 is 2 times g prime at 2 minus g of 2. And we're going to divide this by 2 squared. Now we're going to substitute in what g prime of 2 is and what g of 2 is. We have 2 times g prime. Let's pull this down so you can see it. G prime at 2 is minus 4, minus g of 2, which is 4. And we're going to divide all of that by 2 squared, which is 4. So we have a lot of 4's here. Let's see. 2 times minus 4 is minus 8. We subtract 4. Divide that by 4. This is then minus 12 divided by 4. And we end up with an answer of minus 3. Let's now walk through some examples where we are going to find the given limit. Here's our first example. We want to find the limit of sine of 5x divided by 3x as x approaches 0. The first thing that you always want to do whenever you're given a limit is substitute in the value. So let's go ahead and let's do that. If we let x be 0, we get sine of 0 all divided by 0. Sine of 0 is 0, so this limit is 0 over 0, which is called an indeterminate form. When you're solving any limit that has a sign in it, you want to utilize the fact that the limit of sine theta over theta as theta goes to 0 is equal to 1. If we look at our limit, I want you to focus on the 5x right here. Think of the 5x as theta. So we need to have a 5x in the denominator. So we can say that this is the limit as x goes to 0 of sine 5x all divided by 3x, and we're going to multiply by 5 over 5 because we can't change the problem and just divide by 5. Now what we're going to do is we're going to shift this 3 and this 5. And we're just going to rewrite this as the limit as x goes to 0 of sine 5x all divided by 5x times 5 over 3. We now know that this limit is equal to 1 because it's just like sine theta over theta. So we have 1 times 5 over 3, so we get an answer of 5 over 3. And that's what our limit is equal to. Let's now work through our second example. This one's a little bit harder than the first one. This is the limit of tangent 6x divided by sine 2x as x approaches 0. Just like we did for our first one, we are going to start by substituting in that x is equal to 0. So this is tangent of 0, all divided by sine of 0. Tangent of 0 is 0, sine of 0 is 0, so we again have the indeterminate form 0 divided by 0. Since we don't have a formula for a limit with tangent, I think the best way to solve this problem is to let tangent of 6x be sine 6x over cosine 6x. So we can write this as the limit as x goes to 0, sine of 6x, all divided by cosine 6x, and then all of that is divided by sine of 2x. Now you can see that we have a sine 6x on top and a sine 2x in the denominator. To evaluate these limits, we need to divide sine 6x by 6x, and we need to divide sine 2x by 2x. So what we're going to do in our numerator is we're going to multiply this by 6x divided by 6x, and then in the denominator, we're going to multiply by 2x over 2x. Let's see what this gives us. This gives us the limit as x goes to 0, sine 6x over 6x times 6x all divided by cosine 6x. We're just changing around terms. And then in our denominator, we have a sine 2x divided by 2x times 2x. This limit is going to go to 1, and this limit is going to go to 1. And then notice that our x's cancel out. So what we're left with is the limit as x goes to 0 of 1 times 6 divided by cosine 6x, all divided by 1 times just 2. Cosine of 0 is equal to 1, so this is just 6 over 2, which is equal to 3. And 3 is the value of our limit. What we're going to do now is walk through an example where we find a given limit. The limit that we are going to evaluate is the limit of 1 minus cosine x divided by sine x as x goes to 0. Let's begin evaluating this limit by just substituting in that x is equal to 0. So we have 1 minus cosine of 0, all divided by sine of 0. Cosine of 0 is 1, so we have 1 minus 1 over 0, which gives us the indeterminate form 0 divided by 0. To evaluate this limit, we have to use two things. The first limit that we can use is the limit as x goes to 0, sine x all over x is equal to 1, and then the one that we just saw above, the limit as x goes to 0 of 1 minus cosine x, all divided by x is equal to 0. When you look at the limit that we've been given, 1 minus cosine x over sine x, you can see that it's similar to these two limits that I just wrote down, but there's no x there. So I think the best thing that we can do to evaluate this limit is divide both the numerator and the denominator by x. Let's go ahead and let's go down here. I'll draw a little arrow here, and let's do that. So this is the limit as x goes to 0 of 1 minus cosine x all divided by x, all divided by sine x divided by x. We can do this algebraically because we're dividing both the numerator and the denominator by x. So it's just like multiplying by 1. You can see then that our top limit, 1 minus cosine x over x, is going to go to 0. So let's just put an arrow here. That goes to 0. And then our limit on the bottom is going to go to 1. So we'll say that goes to 1. So our answer is 0 over 1, which is 0. And that's what our limit equals. Let's now walk through some examples where we are going to differentiate the following functions. In our first example, we have f of x is equal to x squared times sine x. Notice that this function has two pieces, the x squared piece and the sine x piece. So when we take the derivative, we are going to have to use the product rule. Let's go ahead and let's do that. F prime of x is the first term, x squared, times the derivative with respect to x of our second term, sine x, plus our second term, sine x, times the derivative with respect to x of our first term, which is x squared. Now we get that our derivative is x squared. The derivative of sine x is cosine x. And then we have sine x times the derivative of x squared, which is 2x. Notice that we can pull an x term out from both of these. So we can write this as x times x cosine x plus 2 sine x. And that's our derivative. Let's now look at our second example. In this example, we are also going to need to use the product rule because we have a first function and a second function. Our derivative, f prime of x, is equal to our first function, e to the x, times the derivative of our second function, which is cosine x, plus our second function, cosine x, times the derivative of our first function, e to the x. We now have e to the x. The derivative of cosine x is minus sine x. And then we have cosine x times the derivative of e to the x, which is just e to the x. Notice that we have an e to the x term common to both terms, so we can pull that out in front. And we're left with e to the x times cosine x minus sine x. And that's our derivative. Let's now look at our third example. This example also has two functions. The first function is secant x, and the second function is tangent x. Our derivative then is our first function, secant x, times the derivative of our second function, tangent x, plus our second function, tangent x, times the derivative of our first function, which is secant x. This now gives us secant x times the derivative of tangent, which is secant squared x, plus tangent x times the derivative of secant x, which is secant x, tangent x. Now let's see what we have in common. Looks like we have a secant x common to both terms, so we are going to bring that out. So this is secant x, and we're left with secant squared x plus tangent squared x. And that's our final answer. In our fourth example, we have a function, f of x is equal to sine x divided by 1 plus cosine x. This function has a numerator and a denominator, so it is a quotient, and we can use the quotient rule. Our derivative, f prime of x, is going to be the bottom term, which is 1 plus cosine x, times the derivative of our top term, sine x, and then we have to subtract off our top term, sine x, times the derivative of our denominator, which is 1 plus cosine x. And we're going to divide all of that by 1 plus cosine x quantity squared. I think one mnemonic that might help remember this is thinking of the top term as the high term and the bottom term as the low term, and then the derivative is just low d high minus high d low, all divided by the square of what's below. Let's now go ahead and simplify this. This is 1 plus cosine x. The derivative of sine x is cosine x. And then we subtract off sine x times the derivative of 1 plus cosine x, which is just minus sine x. And all of this is divided by 1 plus cosine x quantity squared. Now let's go ahead and let's multiply things out. Our first term gives us cosine x plus cosine squared x. And then our second term, we have a minus sine x times a minus sine x. So that gives us a plus sine squared x. And then we have our same term in the denominator, 1 plus cosine x quantity squared. Let's now look at this expression, cosine squared x plus sine squared x. That is a trigonometric identity, and that is equal to 1. So we have on top cosine x plus 1, and then we have a 1 plus cosine x quantity squared in the denominator. Those terms are the same, so one of them cancels out, and we're left with 1 all divided by 1 plus cosine x. And that's our final answer. That's all for this exam review. I hope it helps you as you prepare for your exam.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.